Process industries provide us with a great diversity of products. Many of these products, such as plastics, chemicals, food products, and pharmaceuticals, are produced in batch processes. In a batch process, close control of operating parameters is essential to ensure safety and product quality. Good control also reduces production cost and increases profitability. Carefully designed systems can provide excellent control of batch processes. In these programs on batch control, we'll look at a variety of systems that can be used to effectively control the critical variables in a batch process. In order to understand their unique control requirements, it's important to become familiar with the characteristics of typical batch processes. We'll look at a variety of processes and discuss requirements for control. For example, temperature is often the most important variable and must be controlled throughout the reaction cycle. Other critical variables may include pressure, flow rate of reactant, and degree of completion of the batch reaction. We'll see how instrumentation systems, from simple to complex, can be used to control these variables in a batch process. But before we get into control, let's first go back and talk about the characteristics of a batch process. What is a batch process? What makes it different from other processes? In simplest terms, a batch process can describe anything that is made one batch at a time. Actually, many of the daily activities you're familiar with are batch processes. For example, making a pot of coffee is a batch process. While this example is fairly simple, it does illustrate many of the steps involved in any batch process. For example, in making coffee, you start by measuring the proper amounts of raw materials, in this case, coffee and water. Next, you apply heat until the water reaches the proper temperature. Then you feed the water through the ground coffee to extract the brew. Your knowledge of the requirements for a good cup of coffee is the key to control of this process. The considerations for making a quality cup of coffee are the same as those we'll look at in industrial batch processes. Control of raw materials, control of temperature, and control of the rate of the reaction. How do these control requirements differ from those of other types of processes? One way to put batch processes in perspective is to compare them with continuous processes. Since you may already be familiar with continuous processes, let's start there. In a continuous process, measured quantities of materials are continuously passed through a reaction vessel at a controlled rate. Products are continuously withdrawn. In earlier programs in this series, we've looked at several continuous processes. We've seen how they are designed to produce a large volume of a particular product, and we've seen how the control systems in a continuous process are designed to maintain the process conditions in a steady state. In a batch process, on the other hand, products are made one batch at a time. Here, measured quantities of reactants are brought together in a vessel or reactor and allowed to react to form products. When the reaction is completed, the products are discharged from the reactor. Then the cycle can be repeated. A batch process is typically used when smaller quantities of specialty products are needed, or when the process does not lend itself to a continuous operation. So, control of both continuous and batch processes is designed to maintain the operating parameters required to produce the finished product, but with this difference. In a continuous process, control focuses on maintaining a steady state. In a batch process, control focuses on regulating the changes that take place. With this general overview in mind, let's look more closely at some key control requirements that distinguish a batch process. One difference is in the way raw materials are fed and handled. In a batch process, exact quantities of raw materials are required for each batch. Because of this, the control system in a batch process must provide a way for volumes of raw materials to be measured. In a continuous process, on the other hand, there's generally a continuous feed of materials, so precise flow control of raw materials is a critical part of the process. Another control requirement for batch processes is controlling the sequence of events or steps in the process. Batch processes usually require a sequence of steps, such as feeding, mixing, heating, or reacting. These steps are determined by the type of process and the product being produced. During each step, variables such as temperature, pressure, reaction time, and mixing rate may change considerably. For example, one step of the process may require a high temperature and another step may require cooling, so control requirements vary during different stages of the process. In a continuous process, however, the set points for process variables usually remain constant. Batch processes generally have specific recipes for each product. Control is designed to implement a particular recipe, but because of the flexibility of the instrumentation, the same process equipment can often be used to produce many different products or product grades. Control in a continuous process, on the other hand, is designed to maintain stability of a process and of product quality, despite changes in process conditions. You might find instrumentation hardware in a batch process that is identical to the control equipment used in a continuous process. However, the applications of this hardware are usually quite different. In a batch process, the product is made in a batch reactor, so the instrumentation system is configured to meet the unique control requirements of the reactor. What are the control requirements of a batch reactor? How can these process requirements be automatically controlled in a batch process? Let's use a familiar example of a batch operation to illustrate the basic features of a batch reactor. Then we'll look at an industrial reactor. A batch reactor, whether large or small, is essentially a pot or a kettle. It's usually closed in some way. A cover keeps the volatile ingredients from escaping into the atmosphere and keeps contaminants from entering the process. Usually there's some kind of agitator. Here, the agitator is a spoon. A batch reactor also usually requires a source of heat or cooling. Most often in the home, the heat source is a burner on the stove. So, with a kettle, a cover, an agitator, and a heating or cooling supply, a basic batch reaction can be accomplished. However, there are ways to make the reactor more efficient. Placing a pot directly on a burner is not in reality a very efficient way to heat whatever is in the pot. The ingredients in contact with the bottom of the pot are directly exposed to the heat, while the ingredients at the top are heated only through heat transfer along the sides of the pot, or through the medium being heated. It takes a lot of stirring to keep the ingredients combined and the heating consistent. A more efficient way to heat the ingredients is to surround both the sides and bottom of the pot with the heat. This is essentially what happens in a double boiler. The hot water in the bottom of the boiler regulates the temperature and also permits the heat to be distributed more evenly. Less stirring action is needed. For some reactions, another way to make a basic kettle more efficient is to pressurize it. As you know, there's a relationship between the boiling point of a substance and the pressure applied. There is a normal boiling point that corresponds to every pressure. By increasing the pressure, you can raise the boiling point, thereby permitting the water to get hotter. That's how pressure cookers work. They speed up the cooking process by increasing the temperature within the kettle. This is accomplished by increasing the pressure, not the amount of heat applied. So these examples may give you an idea of the characteristics of a simple batch reactor. Many of these same characteristics can be found in industrial batch reactors. Let's use this drawing to illustrate. A typical industrial batch reactor is usually a large covered kettle. It may vary in capacity from a few gallons to several thousand gallons. Material of construction is determined by the corrosive properties of the process reactants and products. The reactor is usually fitted with an agitator. In addition to blending the raw materials, the agitator also helps in heat transfer by bringing more of the product in contact with the heat source. The agitator in an industrial reactor is more efficient than the spoon used in our previous examples because it can be used while the reactor is under pressure. A stuffing box or mechanical seal around the agitator shaft ensures a tight seal when the reactor operates under pressure. The agitator speed can be changed using a variable speed drive motor. The reactor is often enclosed in a jacket that allows a source of heat or cooling to be in contact with a large proportion of the surface area of the kettle. There may even be an additional source of heat or cooling in the form of a coil within the reactor. Most industrial reactors also have lines for feeding measured quantities of raw materials, and there's usually a discharge line from the vessel through which the finished product may be removed. These are the basic features of a typical batch reactor. The specific arrangement of the reactor and its control instrumentation, however, depends on the type of process. So let's take a few minutes to look at some types of batch processes. One type of batch process is a mixing and blending process. Mixing and blending is a simple batch process which may not involve any chemical reaction. However, control of process variables such as mixing time, temperature, and pressure is important in order to produce a quality product. Paint making is one example of an industrial mixing-blending process. Most of the cooking you do in the home involves mixing and blending processes. A mixing-blending operation usually mixes ingredients by an internal agitator. In a batch reactor, mixing speed is controlled by agitator motor speed. This is similar to the way you'd control the speed of a household mixer. There's another point about mixing or blending operations that's important to consider. Often, mixing is made easier when heat is added. Here's an example that you're surely familiar with. Try dissolving instant coffee or sugar in a cup of cold water. It takes a lot of stirring and a lot of time. By heating the water, you can speed up the process. In industry, the same principle is used. Heat may be added to speed the mixing and to reduce the amount of agitation required. So, mixing and blending is one type of batch operation, or in some batch processes, mixing and blending may be one step in the recipe. Another type of process that may be accomplished by batch control is separation. Separation is essentially the opposite of mixing and blending. What you're trying to achieve in a separation process is to take out some component from a mixture. An example of a separation process is the separation of oil from water. As this simplified drawing shows, the oil rises to the top of the reactor. Heating or cooling may be used as part of the process to improve the separation so the water can be removed. As you can imagine, in a process like this, agitation would not be desirable. Another type of separation is crystallization. Crystallization involves the formation of a solid from a solution, melt, vapor, or different solid phase. Many medicines are made through crystallization processes. So, what are the key variables in a separation process? As in mixing-blending processes, temperature is one of the important factors to consider. But in a separation process, agitation may be a detriment to the reaction. Now, let's look at another type of reaction that may be done in a batch process: polymerization. While the name may not be familiar, the types of products formed in this process surely are familiar. Many plastics and synthetic fibers are made by polymerization. Essentially, polymerization is a process in which a large number of molecules of the same type are combined to form a product. It may require a combination of temperature, pressure, and a catalyst to enable a polymerization reaction to take place. Another type of batch process involves chemical reactions. A chemical reaction may be thought of as the bringing together of two or more raw materials or reactants under the influence of temperature or pressure to form one or more products. Chemical reactions are used extensively in industry, both in batch processes and in continuous processes. The types of products that are made in batch chemical reactions are diverse, from pharmaceuticals to products such as antifreeze, fertilizers, and pesticides. Chemical reactions usually occur under the influence of temperature and pressure, and like some other types of batch reactions we've talked about, the reaction can be affected by a variety of factors, such as agitation, use of a catalyst, and heat transfer. So, we've looked at four typical types of batch processes: mixing, blending, separation, polymerization, and chemical reaction. However, many batch processes involve a combination of these processes, and often other factors as well. As a matter of fact, a batch reaction may be one part of a continuous process, It's this complexity, along with the unique characteristics of every process, which make batch control so challenging. Let's look at one typical batch process to see what's involved. It'll give you a feel for both the complexity and the uniqueness of every batch process. Whiskey making is a classic example of a batch process. There are several different steps in the process, and several of the types of batch operations we just discussed are involved. In addition, in order to produce a quality product, many variables must be controlled, including quantities of raw materials, temperature, pressure, level, and rate of reaction. Let's begin by looking at the steps involved in the process. First, the ingredients, such as barley malt, rye, or corn, are cooked to extract the starch and sugar. Then yeast is added to produce alcohol. Yeast is a primary ingredient which causes fermentation through enzyme action. After it's fermented, the mixture consists of water, alcohol, and residual yeast. There's a limit to the percentage of alcohol that can be produced by enzyme action. So, to produce whiskey, the alcohol must be concentrated,